Hello, everybody. So, welcome to the inside of my office. Here it is. Oh, yes. Oh, yes. Oh, yes. It's very nice. There's the outside. And we're back to my chalkboard. All right. So, this is just a, if you will, a little quick demonstration on my chalkboard to show you the link in between the binomial I was just talking about and the standard normal distribution. So what you're used to seeing right now in a probability distribution is an x column and a p of x column. You're used to seeing, you're used to seeing a series of random variables that are right here, and you're used to seeing a series of probabilities that all sum up to 100%. Perfect, absolutely. The difference is, with a normal distribution, this is discrete, which means these values here take on values like 0, 1, 2, 3, and so forth and so on. And that's great for things like counting chickens, counting numbers of voters, counting numbers of times things happen. Broken arms at Mount Bachelor was an example we used in class. Number of times Max gets his shoes on the correct feet. It's not good for measurements. For example, between 0 and 1, if x was pounds, 0 and 1, there are lots of numbers between 0 and 1. Not discretely. Discretely, it jumps from 0 to 1. But continuously, a half, a third, a fourth, a fifth, a sixth, a tenth, a hundredth, a thousandth. You get the point. So this is your discrete random variable distribution. You have a smooth continuum as far as a continuous distribution goes. Now I'm going to put 0 in the middle here. You'll see why momentarily. And I'm going to label some numbers out here on the axis, 1, 2, and 3, -1, -2, and -3. You'll see why I'm doing this in a second. I also want to make sure you can see that okay. Yeah, you can see that okay. Now, what I like about this versus that, they are analogous. These are your random variables down here. But they're continuous random variables, which means we don't jump from 0 to 1. There are numbers between a half, a quarter, an eighth, and so forth and so on. -2.5, -2.001, -1.998, and so forth and so on. This horizontal axis is the analog to the vertical column here. Although we don't call these x. Well, I take that back. We can call those x. But in this particular line that I'm about to add a curve to, we call this the z-score axis. So these things down here are z-scores. And I don't exactly know why the letter z is used. I'm not real sure. I'm sure it's got something to do with German. We tend to use the letter z a lot because of German reasons. But this horizontal axis is composed of z-scores. And there are infinitely many of them. With a binomial distribution, for example, there's a finite number. Whatever the sample size is, there is one more value of the random variable. Well, here, these axes technically go on forever. Technically. Just like you thought back in Math 111 or Math 95, Math 105, whatever you looked at, when you graph these things, they go on infinitely in both directions. So the analogy, though, is good. This horizontal axis is analogous to that vertical column. So what's the analog to that vertical column, the probability column? Well, technically speaking, the probability column is going to have to be shown running two-dimensionally away from this horizontal. So think of it as xy, although it's not called xy in probability. This is called the z column, and this is the probability of z column. Okay, so we're going to have, for example, for every value of the random variable, we're going to have a point up top that indicates it. Now, if you remember from class, when we did dist draw, we used that. We would draw a series of lines connecting a series of dots. But those lines were a little bit superfluous. They didn't actually exist. I drew them to connect the dots. This will actually have those quote-unquote lines, but they won't be lines. You'll have a probability for 0. You'll have a probability for 1. You'll have a probability for 2, a probability for 3, and so forth and so on. But you're also going to have probabilities for 0.5, and 0.25, and 0.1, and 0.01, and -0.5, and so forth. And when you list all those probabilities up, what you're going to notice is that they take on a beautiful bell shape. A beautiful bell shape. And that's the whole point, is all these points here represent the probabilities of the z-scores directly below them. So when you list them all, you get a smooth curve. Just like we kept seeing the bell curve show up more and more in class after we ran disk draw. Because as the sample size is increased from 3 to 5 to 10, you actually noticed it in the first video you watched, from 3 to 5 to 10 and up, you see more and more of those points, they smooth the curve out more and more, and you end up with the curve that looks like this. Pretty cool? Pretty cool. Now, the equation of this curve is unimportant. If you want to see what the actual equation is, I can show you in class. It's actually on the old 10-mark bill in Germany. Ridiculous, but actually ridiculously cool. If you're interested, you don't have to worry about it. STANormal will take care of it starting on Wednesday. STANormal is one of the programs I gave you on in class this week. There are some things you can tell about this curve, though. For example, what is the average of this curve? Well, it appears to be symmetric left to right, and it is. That's a function of its equation. It's also a function of it's equal on this side as it on that side. So the average of the standard normal is the value that's directly in the middle of it, which is 0. Pretend that's exactly, I'll just make it exactly equal. I don't believe in video editing. Sorry. So your average of your standard normal distribution is 0. Half the curve is on the right of it, half the curve is on the left. Hey, I just said half the curve is on the left and half the curve is on the right. What does that mean about 0? Not only is it the average, it's also the... That's right. It's also the median. It's also the median. And since it's the highest probability above 0, that means it's also the mode. Now, of these, you might be asking yourself, 0 what? What is the 0? The 0 doesn't have a unit. It's simply a scalar. And we'll talk more about that momentarily. So you've got these beautiful measures of center that are related to the bell curve. I want to clear a little bit more space over here. So we don't need the discrete anymore. And you know what? While I'm at it, I want to erase the median and the mode. We don't use those too terribly from this point on. Usually it's the average. Although you're not going to be too upset about that because they're all the same value anyway. And we can use more computational methods with the mean, so we're going to head and use that. So your average, mu, of the standard normal is 0. By definition, the standard deviation of the standard normal is 1. Again, not 1 unit, not 1 anything, not 1 inch, not 1 pound, not 1 degree. Just 1. That standard deviation, combined with the fact that you've got a bell curve, implies that you understand some percentages. And they're the percentages you've always seen from our class till this point. For example, if the mean is average and the standard deviation is equal to 1, you know, remember from class, that 68% of the data lies within 1 standard deviation of average. What does that mean? It means if I throw up a vertical line right there from -1 and up here to +1, that means that if I shade between those values, I have just shaded 68% of that curve. That's what that means. Now some of you might be wondering what the 68% means. Like, how, okay, you keep telling us the 68, and you've showed us that we can count the data points and there's 68% of them are in there. Where does the 68 actually come from? Great question. If you didn't answer that question, you could fast forward over this part. The 68% is a function of what's called a Riemann sum, which means if you were to actually compute the probability of -1, the probability of the z-score directly next to -1, and then directly next to that one, and then directly next to that one. Now, some of you are sitting there going, Rule, what does directly next to -1 mean on the right-hand side? Is that -0.99999? The answer is yes. 0.9 repeating. And then the next one closest to that is 0.9 repeating infinitely with an 8 on the end. And you're probably beginning to think, this is ridiculous. How can you even talk about next to infinitely? You have to use something called an infinite sum on infinitely skinny rectangles. But when you get done drawing these infinitely skinny rectangles, essentially what you have done is you've shaded that entire region. That's calculus in 45 seconds. I encourage you to take any kind of calc class or check out the enrichment page of the website. It's got a much better explanation than what I just did in, like I said, 45 seconds. Okay, one standard deviation gives you 68%. So that right there is 68%. If you bump it out to 2 standard deviations, here to here, that, including that 68%, gives you, do you remember? 95%. So 95% of the z-scores in the standard normal distribution are between -2 and +2. If you bump it out to 3, to -3, what color haven't I used yet? Orange. Essentially, you've got 100%. We often used 100% as a rough estimate of how much we just shaded back in the day. It's closer to 99.7% because, as you see from this curve, there is room on the left outside of -3 and there's room on the right outside of +3 for more data. Your outliers are defined to be the ones outside of 2 standard deviations. And since 95% of the data is within 2, that means 5% is outside of 2. If 99.7 is within 3, that means the 0.3 is on the outside. So half of it on that side, half of it on that side. And that's what I want to kind of get into more using sto-normal. These areas that I'm throwing up there, though, are extraordinarily specific. 68, 95, 99.7. The reason for them, as I said, is due to calculus and the Riemann sum. But I don't want to get focused on that. I want to get focused on how we can turn these percentages and other percentages into usable stuff. Like, for example, we're going to look at IQ measures. We're going to look at pregnancy lengths. We're going to look at, what else are we going to look at? Shower heights at Ramada Inns. We're going to look at seats on airplanes. All of those are actually going to have a unit down here. So we're going to go back to calling that the x-axis. But the idea is we want to get those x's to turn into these z's, because this z curve we know the percentages on. So that's kind of the point. We want to get this curve, comfortable with this curve. And what we're going to use is we're going to use the normal program that I gave you guys at some point, either today's Wednesday, Wednesday, May 15th, or Monday, May 13th. So you're watching this video at some point, maybe on Monday, maybe before Monday. We'll use that program in class. I just wanted this to kind of show you what you're looking at. So what you are looking at is a distribution that is perfectly balanced over an average of 0. Somewhat arbitrary, but that's by definition what it's centered on, by function of the function. And it has a standard deviation of 1. So every time you go out 1, you're picking up 1 more of these little sigmas. What we're going to see on Wednesday of next week, a week from today, is there's a predictable amount of percentage you pick up as you go out standard deviations. You're already familiar with it. Okay? Each standard deviation, as you dive off on the curve, depending on where the standard deviation is, adds a certain amount of area. And we'll manipulate that much more once we're together in class using sto-normal. I was going to use sto-normal here on the videos. I don't think it's a good idea. I think it's too squirrely unless we're all together. I think it makes more sense for us all to be together to use it. And we'll make a video, of course, that day. So that's your introduction to the standard normal distribution. What I want to show you now is one of the ways to use a z-score to use a z-score to convert from a raw score down to this horizontal axis. Basically, what I want to show you is I'm going to show you a comparison between 2 data sets that are on 2 very different curves, and how to get both of those very different curves down to this one. So hang tight, and we'll get to that one next.